One of the most important concepts in neuroscience and understanding what goes on in the electrophysiology of neurons is the concept of the equilibrium potential. And so the equilibrium potential will help us determine which way ions move into or out of a cell. And so we're going to explore this important concept. And in order to do this, we're going to set up sort of a simple situation in which we have a cell where the cell is electrically neutral. Let's say it's at 0 millivolts. And what we mean by that is the outside and the inside of the cell are electrically equivalent. There's no charge difference between the outside and the inside of the cell. And we're going to explore this by first of all looking to determine what is the equilibrium potential for sodium. So the way we would write the equilibrium potential for sodium would be big E and then sub Na. So that would tell us we're talking about the equilibrium potential for sodium. So we start out with the cell at 0 millivolts, and we're going to start out with a situation in which we have a lot of sodium outside the cell, and this is actually the case within a cell. And so representing the sodium is going to be some little yellow cubes. We have a channel for sodium here, so sodium could potentially move. And we have very little sodium within the cell. Now, at this point, you can see there's a little bit of a problem here. There's a lot of sodium outside the cell, and there's little in. So we have a concentration difference. And that concentration difference produces a force that is based on that concentration difference. And it's a force that would tend to drive sodium into the cell. So I'm going to draw an arrow into the cell, and this is the force that would tend to drive sodium into the cell. And so because of this force, we're going to move some sodium into the cell. Now, as we do this, the cell is going to become slightly more positive. We brought a positive charged ion into the cell, and so the cell may go from 0 millivolts to, let's say, plus 5 millivolts. And so obviously one single ion is not going to do this, but each one of these boxes or little cubes represents a lot of ions moving. Now, as we do that, we're going to have a little bit of a situation occur. And that is, as we move in positive charge, we now have a situation where the next ion that wants to move in has a positive charge, and it wants to move into an area that has a positive charge. And so just like you learned in kindergarten, if you have two positive magnets, they tend to repel each other. If you have two positively charged ions, they tend to repel each other. So there's actually a little bit of force based on electrical energies that would counter that movement of that next ion in. But as you can see, the concentration force is still larger than the electrical force, so that sodium will enter. As it does that, the cell becomes slightly more positive, and our electrical force that would oppose movement continues to build. So every time we bring in some sodium, it becomes a little bit harder for the next sodium to arrive. Until at some point these two forces are balanced. And at that point we are at the equilibrium potential. So the equilibrium potential has a few key things about it. So first of all, the two forces are balanced. And so what that means is an ion is as likely to enter as it is to leave. So there's no net movement, right? There's no reason for an ion to move into the cell that's any bigger than there's a reason for the ion to move out of the cell. So again, things are still moving back and forth, but there's no net movement. And the second thing is that this equilibrium potential allows us to predict the behavior of this particular ion. So ions are always going to move to reach their equilibrium potential. So, a general equilibrium potential we'd say was Ex. If we're talking about sodium, we'd say that sodium will move to try to reach its equilibrium potential. So that's the situation for sodium. Let's try the same thing with potassium. So for potassium, we're going to use red cubes. Again, we're going to arbitrarily set our cell at 0 millivolts. There's no difference between the outside and inside the cell. We're going to put down some cubes for potassium. Now, potassium is highly concentrated inside the cell, so we have a lot of red cubes inside the cell. It's not particularly concentrated outside the cell. So we have our higher concentration inside the cell than outside. It's about a tenfold difference. So as we can see here, now the force of concentration would tend to have potassium leave the cell. So let's say some potassium leaves the cell. Well, as that happens, because we're removing a positive charge, the cell is going to become a little more negative. And again, we're using these cubes to represent a lot of movement, so any one particular ion movement is not going to change the cell drastically, but this would represent a lot of ions moving. So the cell is becoming more negative. Now, if we have another ion leave, right, we have a situation where, again, this area is relatively more positive than this area. So the ion really doesn't particularly want to go out here. And this is a nice little negative zone that the ion would prefer to stay in, right? Remember, negatives and positives attract. So just like we had previously, there is a concentration force, or I should say an electrical force, that tends to oppose the movement of potassium out of the cell in this particular case. So just like we had before, this is smaller than this, so we have an ion move out. But every time we move an ion out, the cell becomes a little more negative, and the electrical force that would tend to have potassium stay in the cell starts to increase. Right? And this would keep going and going and going, and at some point the two forces would be balanced. And so we have now reached the equilibrium potential for potassium. Again, it would make the cell be negative. It might be something like minus 80 millivolts is a typical value. But at this point, these two forces are balanced. Again, potassium can come in, but it's just as likely that potassium will leave. There is no net movement. And ions, again, have moved to the point where they're going to get to this equilibrium potential. Now, the equation that governs the equilibrium potential is called the Nernst equation. You guys can look this up if you want to. Looks like a long, gnarly looking equation. It's actually fairly simple if you understand what's going on, but one of the major things you'll notice if you look at that equation is that if there's a smaller difference between the two different areas, or a larger difference, that greatly affects the equilibrium potential. So let's take a look if there's almost no difference for sodium between outside and in. All right, so very much closer in concentration outside and in than we started before. So first of all, concentration difference is smaller. Right? There's not as much difference before. So again, every time we start to bring some potassium, I should say sodium in, it doesn't take very long for us to balance these two things out. So it should go this way, okay? So because there's not as much difference, the concentration force is smaller to begin with, and so it doesn't take as long for us to get to the electrical force. So in this particular case, ENA, which might have been something like plus 70 millivolts, is not as positive, right? Now it might be something like plus 30 millivolts, okay, just because the forces are a little different. Let's take another example. And again, we're going to deal with ENA, but we're going to say that we have a lot of sodium outside the cell, right, and very, very little inside the cell, okay? And so again, we're starting at 0 millivolts. Well, if we look at this situation, there's a huge concentration difference. So the concentration force is larger than it was before. So we have to move in more charge than we did previously to balance that out. Right? And as we move more charge, the cell becomes more and more positive. So again, the cell might have been plus 70 millivolts, I should say EK might have been plus 70 millivolts, but in order to balance out this bigger concentration force, we need to make the cell more positive than it was before, something like plus 100 millivolts. So again, if you look at the Nernst equation, there's things like temperature that have an effect on this, but the biggest thing that changes on a physiological level is the concentration of ions. And you can play around with the Nernst equation. You'll see how important the concentration of ions inside versus outside is to the equilibrium potential.